All right, welcome back, Yay Notes. So, today we are talking about stars and the life cycle of stars, how stars are born, how they live. Then, they get old, they go to that retirement community. Some of them just kind of burn out. Others like to go out with a bang. It's all kinds of fun. And we're going to learn all about it today. Now, we classify stars based on these 5 things: composition, brightness, temperature, mass, and the life cycle. And that's going to determine how it all works. All right. So composition. It is the makeup of the star. Now, stars are made up of different things. It changes the way they burn. It changes the light that they give out. So, I know none of you have ever been up next to a star. I haven't been up next to a star yet. Would be kind of cool. But everything is so hot there that it's in the form of gases. And that just makes sense. When things get really hot, they become a gas. Well, everything in a star is so extremely hot, it is made up of a gas. And these elements, they're burning, they're fusing together. You'll get 2 hydrogens, and it's so hot that they fuse together to make helium. They release a lot of energy, and they make it hotter. Whoa. And that is what produces our energy that we get here on Earth. Now, if you use a spectrograph, these gases can be identified. It's what we talked about yesterday when we talked about the absorption spectrum. How you get those funky little lines going up and down. So that's what a spectrograph or a spectroscope will show you. Which specific gases are being burned. It's going to look like this. So over here on the left, we have a continuous spectrum. This is when all of the colors are there and are present. Now, an absorption spectrum is going to have some blank spots in it. Right here, you can see the different lines that are in it. And based on which lines are there and which lines are gone, that tells you which gases are there. Easy stuff. All right. I believe that does finish off the first page of fill-in notes, yes? Yes. Now we're on to the next page of the fill-in notes. So continuing on. Brightness is the next thing. Now, here are 2 amazing vocabulary words: apparent magnitude and absolute magnitude. And it is a little different. Apparent magnitude is how bright it actually looks from Earth. And aren't there things on Earth that change the way the stars look? Sure. Maybe, sure, probably. Heard a bunch of different things. So, spend about 15, 20 seconds. Come up with at least 5 things that change the way stars look. Go. All right. So, I heard a few of the things that you're talking about. I do have a question for you. Because all of you live in Frisco now. You've probably been in Frisco a while. And Frisco is not the same place it was when I moved here. When I moved here, the tollway was just a 2-lane road. 121 was just a 2-lane road. And everything here was just farms. At night, I would look out, I would see stars everywhere. Now I look out at night and I see 3. Can anyone guess why there is a difference? Yes. City lights. Anytime you're around city lights, that will definitely drown out the light of the stars. It'll block it out. You can't see it. Kind of hide it. Anything else? No one else? Yes. A little bit of pollution. Do you think that's going to get in the way? Yes. Definitely going to have something to do with it. Have any of you ever gone out into the country and looked at the stars? Any of you, something that's very popular with my students, they tell me they go on cruises and they'll look at the stars when they're on a cruise ship. Any of you ever done that? Couple. So it's amazing when you get out there, you see the stars, and you're like, oh my gosh, how can you find even one? Because there's like thousands of them out there. But here you see like 3. So yes, the apparent magnitude, how bright it looks, that gets changed because of these things. A lot of the telescopes that we use that are Earth-based have to be in extremely remote locations. The reason is they can't let all that, the light, the city, things like that, interfere with what they see. It changes what you see. It's another reason we have the absolute magnitude, how bright it actually is. The Hubble telescope gives us an absolute magnitude. Y'all know what the Hubble telescope is?
The telescope in outer space.
It's the one in outer space. It doesn't have those pollution issues. It doesn't have the atmosphere issues. Because of that, it can give us an absolute magnitude, what it actually is. Yes?
What are parsecs?
It's a distance.
But like, how big?
Pretty big. I don't have the specific number.
Because like light years are crazy.
Light years are crazy, and we will be talking about light years in the next 2 days.
So parsecs would be smaller than that, right?
All right. Next up, temperature is our next characteristic of stars. Temperature is determined by the color of the star. And it's classified by a single letter category, O, B, A, F, G, K, M. This is not something you're going to have to memorize, but this is something, this type of table is something you're going to have to be able to read and understand and follow. So it's very likely on assessments that you'll be given something like this and asked to figure it out. So what is the hottest star that's up there? The blue star is the hottest. It's detecting helium in there. So helium is actually fusing, coming together. What's the coldest star?
Red.
Okay. Doesn't that go with that energy thing I told you yesterday? What color has the lowest energy? Red. What color has the highest energy? Whoa. Roy G. Biv. Another thing. Anyone know what our star is?
It's red.
What is our star? How do you know what our star is? Oh, look right there. It's letter G. Has a surface temperature of 5,000 to 6,000 degrees Celsius. It's pretty hot. It says it's the sun. The HR diagram. Hertzsprung-Russell diagram. We're just going to refer to it as HR, and we're going to have to be able to read this. It is a bit confusing. Some of it seems like it's backwards. For example, on the bottom, if we look way down here on the bottom, so right down there, those are temperatures. And those temperatures on the left side of the graph, right here, can anyone read what that says? I know, you're a little bit far away, so it might be hard to see it. Yes, what does it say?
Is the axis spectrum type?
We'll get there in just a second. Hold on.
Oh, wait.
So right here, what I want to know, anyone, can you see what this temperature is?
Oh, yeah. 30,000.
30,000 over there. What's this temperature over here on this side?
30,000.
3,000. So we actually start over here on the left with the high temperatures, and we finish on the right with the low. And that's kind of backwards. Most of the time when we do a graph, isn't it the other way? So a lot of people are looking at this incorrectly. You have to make sure you look at the numbers to see which way it goes. The other thing you can look at is the color. What color do we know is the hottest?
Blue.
And blue is right there. What color do we know is the coldest? Red's over here. So if you look at that, you can see the difference in the temperatures without looking at the numbers. All right, so this HR diagram is based on absolute magnitude. Now, which one's that? Is that the one that we see from Earth or the one we see from space? It's the one we see from space, the one it actually is. All right, so this is just a simple HR diagram. Over here on this side, it has brightness, and on this side, it has temperature. Notice the temperature is still decreasing as you go this way, but brightness is increasing as you go this way. Make sense? So if you want something that's very bright, it's going to be near the top. If you want something that is very hot, it's going to be to the left. So the hottest and brightest is right there. The coldest and dimmest is right there. Last but not least is mass. How much stuff is actually in the star? Now this one, you don't have this on your paper. I want you to draw the life cycle of the star on your paper. So I definitely want you drawing the life cycle of the star on the paper. You have some space at the bottom. That would be a good spot for it. If that's not enough space for you, by all means, get out your own paper. So what we're going to start with is a stellar nursery. It's called the nebula. A nebula is just an area that has a lot of gas, a lot of stuff just kind of sitting out there hanging out. So a nebula is all this stuff just kind of hanging out. When you get all this gas close enough together, it's going to start to form its own gravity. Because gravity happens anytime any two things get in proximity of each other. And they start attracting towards each other. And then they attract some more gas towards them. And once you get enough stuff all together, you're going to move on from a nebula into the next phase of life. And our next phase is completely dependent on just how much gas you get to start with. Next thing we're talking about, most powerful energy source in the... Actually, before we talk about quasars, we're going to go back. Sorry about that. I want this one. So, we have our nebula, we had all this gas here, it started to form its own gravity. If it's a smaller amount, and that's a relative term, smaller amount, because either we have normal or we have massive. So right up here, this side, oh, that's not a good color. Let's try that one. This side right here is a normal amount of mass, okay? So this is a normal on the top. This is a massive amount of gas on the bottom. So you either have normal or massive. If you have a normal amount of mass, all that stuff comes together, it ignites, you have a normal star. As a normal star burns, it becomes a giant star. So it goes through its normal life, and then near the end of its life, it starts to expand and expand more and expand more. And that's called the red giant stage. So, had all this hydrogen, it's burning hydrogen making helium. And as that helium fuses, it makes other things like lithiums, carbons, things like that. So the heavier elements, getting a little bit heavier, not a heavy element, just heavier, getting bigger, and it expands. As it's going, as it expands, it cools. Because it has that same amount of heat, but it's taking up more space. And then all of a sudden, it expands so much, it doesn't burn anymore. It flashes out, and you have another nebula. And what you're left with, in the center of that nebula, all that extra gas just kind of spreads out, and in the center you're left with a white dwarf. So this was the core of that star. Yes?
I can't see what's on the bottom.
We're on the top line right now.
Oh, okay.
And then we'll get back to the bottom in just a second. So we have the nebula. Then we have a white dwarf. This is the core of that star. Now think about this. If you had something in the oven, and you had it in there, it was baking at 400 degrees, and you had it in there for 2 hours, and then you just turned the oven off. So you turned off the heat. Would you want to go in there and grab that pan?
No.
No. Why not?
Because it's still hot.
So this core has been inside a star for millions of years. You think it's still going to be a little bit hot? Even though the star is not burning, think it's going to be hot? It's going to be hot for a while. Not a trick question. But will it cool off? I mean, if you left that pan in the oven for a day, would it cool off? Yes. Well, if you leave this core just floating out there in space for a while, is it going to cool off? And that's what the black dwarf is. So the white dwarf is when it's still hot because it was burning for so long. But when it cools off, it just becomes a chunk in space called a black dwarf. And this eventually is what's going to happen to our sun. So our sun is a normal, average star. It will become a red giant. After the red giant stage, all those gases will puff out and they'll flare out. We'll have a nebula there. It'll be a hot white dwarf, and then it will become a black dwarf. Now, not all stars are like this. Some of the stars have more gases to start with. They are giants. So a giant star has over 3 times more mass than our sun. And our sun's pretty massive. This is 3 times bigger. So this huge giant star burns. It burns hot, it burns quick. And then instead of becoming a red giant, it becomes a super giant. So it goes from normal to super giant. After that, it's going to blow up. It will explode. That's the supernova. So will our star ever supernova? No. Our star will not supernova. Our star will become a nebula, but a giant star is the one that can become a supernova. And from there, it can become a neutron star or a black hole.
Wait, so what are the second line, not the third?
We're on the bottom.
All of them, not one.
And right here, you have a choice of going there or there. Black hole or neutron star.
What about there, those huge stars are there?
Okay. Quasars. This is an enormous amount of energy all stored up in one place. It's the most powerful thing that we know about in the universe. These are considered to be the core of a galaxy. So you remember looking at those galaxy pictures the other day. we saw that really bright, dense area in the center. That's called a quasar. And these are very distant, so we don't know a whole lot about them, but that is our current theories on what a quasar is. Last but not least, comets. We had a lot of discussion in some of my classes yesterday about comets. They are actually ice, dust, and gas. And it looks like they have a tail of fire going behind them, but it's not fire. What it is, it's all the dust, the gas, the ice is trailing the comet. Solar winds will push these things away to make the tail. All it does, it's not burning, it's not making its own light. Just like the sun, or just like the moon, it's going to reflect the light of our sun. So it's just a body in the space, and it's on a path, a rotation around planets, around the sun, completely gravity driven. So there we can see a comet actually going around the sun. And that's what it looks like on the right side.